Did I do the example of heating water through the microwave last time? There I think I got 99, and that's because it's a lot simpler than weighing trucks in motion, all right? I don't think this is such a bad value. It's pretty good. I'm not sure, given all the things that influence electronic devices and trucks that weigh 20,000 or more pounds, I guess up to 40,000 pounds, don't get in their way. I think that's not too bad, okay? Now, so we have a fairly strong relationship. It's a positive relationship. I would say to write a few sentences telling what the plot says about the data. Well, the thing that I notice primarily is what I said before. We'd like this to be pretty close to 0, this to be pretty close to 1. And again, you could do this electronically, so I would assume that that's what they've done. All right. I suspect this data came from, it could have come from actual measurements. Some company said, have we got a new thing for the Department of Transportation? And then they say, okay, let's test it out. And what they would have done is they would have gone back to the shop, readjusted their devices, and maybe tested it again. Okay, it says find the correlation. I found the correlation, 0.96. It says if the trucks were weighed in kilograms, how would they change the correlation? Changing units does not change correlation. Now, let me just qualify that a little bit. You have to change both, let's see. Well, actually, you only have to, you can change just one or two. And the reason for that is actually your computation takes place via the z values. If you go back to how we compute the correlation, all that we're doing is we're doing the z values. And the z values are uninfluenced by the changes in the units that you use. Now that assumes that there's a linear relationship between kilograms and pounds, and in fact there is. Okay. F, do any points deviate from the overall pattern? What does the plot say about a possible recalibration of the weights in motion? Okay, first of all, I would say generally the relationship is quite strong. That where we see the deviations are primarily at the upper weight limits. Now, depending upon all the various electronics and mechanicals and so forth and so on, and actually it would probably be more electronics, but I'm not, it could be a lot of stuff. They might be able to tweak things so that these higher values, in other words, we would get better estimates, if you will, of the higher weighted trucks by doing various things through the devices we're using. Anytime you use electronic devices and you're going to measure something, they have to be calibrated. I suspect that on some regular basis, in fact, this would also be true for the traditional way, the static weights, they would have to recalibrate them periodically. I don't know how often that would be done, but that's typical for any time you're measuring something in science, engineering, your devices get recalibrated. Excel. This is a formula sheet. This is a table. You can use your calculator. I think okay. All right. So I think that's pretty much. It does look to me that this needs to be recalibrated. And again, how they do that is, it's an engineering problem, but this would work just fairly well. We probably want to see if we could improve the weights at the higher weight levels. And that may not be easy to do. A lot of this stuff is easy, it's easy in principle. There's an expression I like to use. In theory, there's no difference between theory and practice. but in practice, they're sure as heck is. Okay? So just because it's supposed to be nice doesn't mean, in fact, it is. And that's basically how most people who work in, engineering, the science, building trades, is they take the ideal and try and make it real. Even including houses. The lumber warps, things come in at the wrong size. Everyone's all trying to fit the ideal, take the real stuff and make it fit reasonably well with what was intended. Okay, questions on number 40? Yes?
So you would really consider that a deviation? It seems to me that that last one is so close to the line.
Okay. A difference is a difference only if it makes a difference. Who would be interested in correcting for this? And who would not? The thing is, this is what's happening here. Let's look at the numbers themselves. And what I'm going to do is I'm going to put my cursor above that, and let's see. So I have, all right, the one that said, it says 39.5, okay. So I have a truck where the weight in motion is 39.5, but in fact the static weight is this. This is where interest comes. The trucking companies don't want to be charged if they're charged by this amount when the true quote-unquote rate is 38. Okay? So, in this case, all right, it would be in the interest of the commercial truckers to try and do something to the electronics, whatever, to bring that closer, so that it's closer to the real value. Now let's take a look at this one, 40, okay, this is, all right, this one is associated with this. Now, if we use, well, let's do the one. Suppose I have a trucker and the newfangled device says, oh, you're carrying 40,000 pounds, when in fact the real weight is 35,000 pounds. I would guess the interest would be in the terms of the trucking companies to make sure that whatever happens, whether you deal it this way or some other way, this is a lot closer to that. Especially if there are fines or taxes or anything associated with that. This is why people recalibrate things, because things get out of tolerance. Now when you go into a grocery store and you buy some meat, or you buy some produce, buy the pound, whatever, most of those instruments will be calibrated on some regular basis, and I don't know whether it's a monthly basis or a yearly basis, and it gets all the way traced back to a kilogram in France. Now, it's a very complex process between the kilogram in France, which is the kind of standard kilogram, and the weight at the grocery store. And that's all mediated by the companies that sell the weighing devices, by the National Institute of Science and Technology, and there may be some state organizations in between. So there's a lot of things that go on, but you know, when you buy something at a store, if it says this is 2.5 pounds, you want to make sure it's 2.5 pounds. Or at least on the meat count. What about the grocery, or the cereal boxes? That's a different ballgame. This is what happens. The value that's stated on the box, I would guess, is almost always exceeded by what they give you. Because if they give you what's on the box, they've met their legal requirements. And what they can do is say, we're giving you 18 ounces, knowing full well sometimes it's going to be a lot more than that, and they just adjust the price. It's a lot simpler. I have actually done some measurements here, and it does look as though, and it makes sense, that if it says a certain number of ounces on the can, or the box, whatever, the company is in better shape if it says that it's over as opposed to under. If it's under, you get in trouble with the press, the Federal Trade Commission, who knows, loggers, there'd be a revolution in this country. Well, maybe not quite. But, so a company, depending upon what your strategy is, on a cereal box, they probably give you more than stated on the box, just because in the long run, it's easier for them to do that. There's less risk involved. Whereas at for meats, produce, and so forth, there's more of an interest to get it close to what is stated. All right. Again, I don't work. I kind of know a little bit about this, but you can also realize your interest involved here. Sometimes the interest is not so much in being accurate as it is in getting more than what they say you're being given. Like all those bonus points you get when you buy this, so you can buy more stuff. Kind of like that. All right. Let's take a look at the overheads here. And let's see, let's go back. That's a little too far. Okay. Well, let's just take a quick look here. Linear relationship, R is positive. Linear relationship, R is negative. We have a value of R, but it's meaningless. This is a quadratic relationship. Here I have a line going through it, but it's all scattered. So that R has to be a small value in magnitude. All right. This is the notation I used over here. The reason we use Y hat is because what we do is we can take the X value or the explanatory value and compute a predicted value of Y. The predicted value of Y is not the real thing. We go back to the here. This is not the real thing. Here, what we're trying to do is get to the real thing, okay? And basically the way we do that is through this equation, all right? Now, what we should do here, let's do this. I'm going to move this to the right. Let's determine what Y hat is. Okay? So this is, what I'm going to do is I'm going to use this equation right here. And I'm going to compute what I think is the true weight, all right, based on this measurement. So what we do is the following. B0. I think I'll use the value here in the graphic, 10, 0.854 plus, now the slope is 0.6379. Did I get that right? Yeah. And what I want to do, I want to multiply that, so I enter in the asterisk, times the measurement. All right, so I do this. So once I get done massaging the data, calibrating it appropriately, this turns out, the truck goes by, has that reading on, and then I do the correction for it, and it says it's 27,000 pounds. That's not too bad, I don't think, as far as estimate is concerned. Now what I'm going to do is I'm going to scale this all the way down here. And I think what we'll do is, rather than having all that precision, I'm going to change the formatting so I only have one decimal place. So this device, once we've corrected corrected for these measurements using our regression line, truck goes by and we charge them for fees or whatever. We think there are 27,400 pounds, whereas the static weight, presumably the better measurement, is a little bit more than that. Now here I have, again using this corrected formula, I'm predicting the weight of this next truck is 29,900 pounds, okay? Next one, this truck here, its weight is estimated against, once we've corrected for everything, to be 36,000 pounds. That's a little bit less than this, and so forth. So that's Y hat. Now, what is what we call the residual? Now what I'm going to do is I'm going to take this is what was true if it were that. In other words, that's the static weight, and I'm going to subtract from that the predicted weight. And then I'm going to extend this all the way down. All right. Now, once we've done all this calibration, the residuals, you see the residuals are, well, the largest residual here is about 2, so it's off by about 2,000 pounds. So this is the value Y hat I'm getting from sticking this value here into this and coming up with what I think the true static weight is. I take the true static weight, subtract from Y hat, and I get those numbers. That's the residual. All right, so we've talked about this equation here. We've described about how we get the regression slope and Y-intercept. You can take a look at that. Excel did all the work for us in this case. Now what I've done here is I've actually replicated this table. I had the explanatory variable, which was the weight in motion. I have the response variable, all right, and I have the predicted value, and I have the residuals. So I computed all. Basically, this is given, and I computed these two columns. Now note that each one of these columns actually has a standard deviation and a mean. Now this notation over here looks a little weird, the predicted values, so I have a Y hat and above that a bar. That means the mean, if you will, of the predicted values. S with a subscript of Y hat, that means the standard deviation of the predicted values. R squared is a theorem that says R squared is the ratio. This is the variance of the predicted values. This is the variance of the observed values. This ratio, the closer it is to 1, basically it says the regression line is doing a better job. Okay. Pair of data can be represented in a scatter plot. That's what I did. For scatter plots which appear along a line, an equation of a line which nicely passes through the data may be determined. That's the least squares regression line. There are actually other ways of determining that, but this is the most commonly used method. All right. Again, that's what we call the least squares regression line. The square of the correlation, as I just described, indicates how well the line passes through the data. R squared, let me emphasize two things here. the value of R must always be between -1 and 1. You can show that mathematically. It can never be outside that range. The value of R squared, all right, must be between 0 and 1. If you have a number between -1 and 1 and you square it, that number has to be between 0 and 1. And that's some algebra. I'm simply going to state it. To show that R lies between these two values is not trivial. As a general rule, a value of R will never be 1 for real data and will never be -1 for real data. It can be very close, but it's never exactly 1. If it were exactly 1, well, that would mean is all the points are exactly on one line. Data is never that way. There's too much variability in the universe. All right, now, as I described before, the residual is that which we observed, which in the case of the weights on the truck would be the static weight. We took it onto a static scale and we actually measured it. And then we subtract from that the predicted. That's the value that comes out of our regression equation based on this detection called weight in motion. So it's y minus y hat. Sometimes I put a subscript down here, maybe of I, indicate, well, I can only compute residuals for something I have data for. Now, why don't we use the symbol R for residual? Well, R is already reserved. We use it for correlation, so we have to come up with a different name or a different symbol, and typically we use E. E is a kind of comes from error. Sometimes it makes sense to think of the residual as being an error. If we go back to our weight in motion here, we can think of these as being an error. That was how far off our prediction was from the real stuff. Okay, now, there is an important quantity called the standard deviation of the residuals. And it's symbolized by the letter S, the subscript of E. This is how it's computed. You take all the residuals, you square them. Take every residual, square it, and add all of those together. Divide by n minus 2. Ignoring the radical for the moment, that would be the variance of the residuals. Once I take the square root of that, that's the standard deviation of the residuals. I think I explained last time the reason we divide by n minus 1 is we want to have, the real reason is theoretical, but one way of thinking about it is as follows. If you just have two data pairs, that if n is equal to 2, your line will go through those points exactly. There's no residual to talk about. It's meaningless. So if we're going to use a formula, we better make sure the formula only makes sense when I have 3 or more data pairs. So if n is 3 or bigger, this will be a positive number and our computations make sense. All right, let's take a look at the what's called the residuals plot. And in order to do that, I think I did that for the price of houses last time. Let's do it for this example, number 40. So what I'm going to do here is the following. There are a couple ways I can do this. Actually, let's do it. I'll do it the other way. What I'm going to do here is the following. The residuals plot will be explanatory variable. I'm using this as the explanatory variable. That will be the x-axis, so to speak, or the horizontal axis. and this will be the vertical axis. So now what I'm going to do is I'm going to create a new scatter plot where this will be represented along the horizontal and these values will be represented along the vertical. All right. I did it last time using the data analysis toolkit, but the results are the same basically. So I'm going to come down here and let's see, I want to insert a scatter plot, which is basically just a plot, if you will, of the explanatory variable and, if you will, the residuals, as opposed to the explanatory variable here and the static weight. So what we'll do is we'll select the data, do an add here. The x values are going to be here. Again. And then the y values are going to be the residuals. Okay. Now I could actually plot that just by hand. It's not a real complicated. If you use Excel, it's a lot easier. Okay, now let's get rid of that because that doesn't help me at all. All right, now this is, so this represents, if you will, the explanatory values, and the vertical is represented by the residuals. Now what we look for is to see whether or not there's a pattern here. The only thing that seems really out of line is this thing right here. Okay? And that is associated, I think, with the truck, where the weight in motion was 39.5. Its actual static weight was 38. Our equation says it's 36, so there's quite a bit of difference there, 1.9. Let's see if that's, I think that is the value there. Yeah, that's the one right there. Now, other than that, there doesn't seem to be anything that's terribly broken about this relationship. Part of the problem I see in this data is there's only 10 values. And 10 values is a rule that always seems to me a little too low. Why would you only have 10 values? Well, how many truckers want to be part of an experiment where if they're late, their employers will be mad? I don't know how they got the data. Maybe they had various truck companies, volunteer to participate. Who knows? I don't know. But that's the one that seems a little bit out of line. Now, you can have residuals plots that look something like the following. I think I had something like this last week. So we could have a residuals plot say that looks something like the following. This is our 0. I might have something like this. The problem here is it looks like the residuals are negative for small values of the explanatory variable. Again, the horizontal represents the explanatory variable. The residuals are first negative, that is below 0, then positive, and then again negative. This would suggest there's a nonlinearity involved. That one up there suggests maybe we have an outlier. We might want to focus on why was this truck special? A lot of it depends upon who's doing the measurement and how they're doing it. And a lot of stuff, when you first set it up, you kind of cobbled it together, and you're trying to see whether or not you know what you're doing. And so you have all these people with little wires here and there, and you have a little device here and so forth. And they often will do that so they don't have to spend all the money and get everything all done and figure out they're not really done. Yes?
Last question, but you said that when we do the residual based on this model, it's a linear model, right?
Well, yeah, we only talk about residuals when the scatter plot looks to be along the straight line.
Yeah.
Okay.
How come this residual, this is not, this is plot is not linear?
Well, the residuals plot, what we're looking for is the residuals are the error, the difference between that which we observed and that which we predicted. So we do want scattering. We don't want, we have a nice relationship when our residuals plot looks like it's just buckshot. Take a shotgun and you shoot it at the wall and it just splattered all over. All right? That, you see, if we see that in the residuals plot, that's what's sometimes called a diagnostic. It says, it looks like we're kind of doing the right thing. If, on the other hand, we have a residuals plot like this, this is going to suggest there's a nonlinearity involved. And there's, I don't want to spend a lot of time on this, but the bottom line is when you have, this poses questions, or raises questions. Whereas in contrast, if we have a residuals plot that looks something like this, that means our analysis is probably pretty good. See, what we're seeing here is the following. Let me use this. In this case, there's a kind of pattern here. In this case, there's not much of a pattern. Now, again, what I'm doing is I'm looking at the residuals along the vertical, and along the horizontal is the explanatory variable. This says we need to do more work. Basically, this says there's probably not a lot more to extract out of the information. That's another way of thinking about it. In this case, you might or might not want to do anything more. In mathematics, we only have one answer. In real life, it's more complicated. Whether or not your least squares regression line is useful, valid, and so on, depends upon what you want to do with it. Now, you've done all this work, what are you going to use it for? You know, if you teach statistics, you do it for the pure joy of it. All right? In real life, usually there's a reason behind this. And then the question would be is, do I want to fix this? Do I want to look at this using maybe a nonlinear relationship? Yes?
Start on something kind of basic. For the equation for residuals, we're doing y minus y hat.
Right.
We use x minus y hat.
Oh no, we use, okay, let's go back. Okay, let's go back to, in the beginning, I only have these two columns. All right? The one on the right, if you will, is the measurement which was taken from the kind of traditional way of weighing trucks. They pull up, and there's actually a scale underneath them. It's been calibrated. They get a measurement. All right? One way of thinking about it is that's the real stuff. That's the golden measure. That's
Is that the x?
oh, pardon?
Is that the x thing?
Yes. So the weight in motion is our explanatory variable, and let me put it in parentheses. This is our x. Now the weight of the actual static
I think I see now that we
Okay.
did y minus y hat. I guess maybe I'm still not sure why, like, if I had just looked at the data and tried to decide for myself which was x and which was y, I probably would have done it.
Yeah, you might, yeah, I can see that. See, the question here is the following. What do I want, what measurement do I want to use for some purpose? What I want to do is the following, is I want to get the measurement from the weight in motion and somehow compute a value that will be very close to the true value. Okay? So, the word explanatory sometimes has some limitations, and I think that's probably the case here. We're actually using x as the one, we want to use x to do the predicting of y. Okay, in this equation, we're going to take some measurement that comes out of our electronics in some way. We're going to stick it in here and come up with a value here. Now, this value here is represented by this column. This right here is represented by the y hat column. Now, this is the y value. Let's go back to the houses. In the case of the houses, we had square feet. In that case, square feet is relatively easy to do. It's a relatively solid measurement. But so is the price of a home. The price of a home is registered at the county clerk as a rule. Now, in that case, we're using the number square feet in a way to predict what we think the price of a home should be, even though we know exactly what the price is. In this case, we're using the weight in motion in order to predict what is the true weight. Okay? So, the way in which we're using this is the explanatory variable, this is the response variable, and this is the predicted value. Okay, so now, for the residuals plot, try and fix this a little bit better here. You can see everything on the screen. All right, so we're not too bad here, but all right. This here is based on these values. From that, we get our least squares regression line. From this, I compute this using this value alone. The residual is this minus that. That's this column right here. Now, what I've done down here is I plotted these values, which are the residuals. So I'm using this along the horizontal and this along the vertical. When I look at this, the only one that seems a little out of place is this here. That's where we want to focus our attention. We're the Department of Transportation, or maybe the trucking industry. Over here, if we saw this, we would see one. This is not maybe obvious, but there is a pattern here. The pattern looks something like this. What that suggests, again, it's not obvious, there's a nonlinearity going on. This poses questions. This here looks as though I just threw things on the board, or took a shotgun and shot it. There's no pattern here. When the residuals look like that, that means I've extracted as much information as I possibly can out of my data, and there's no point in proceeding any further. We're done, in a way. So this says the regression line looks to be pretty good. There's no more information to be extracted out of this. So we declare victory and move on to some other. This here would say, we have to investigate. Why is this happening? There does appear to be this pattern. And over here, about the only thing that suggests, at least to me right off the top of my head, is this value seems to be a little bit off. We might want to go back, and there are a couple of things you might do. You might look at when the measurement was taken, who measured it. It could be, again, depending upon all the circumstances that are involved in measurement, some people are a little better at using instrumentation than others. The people have been around for a while, they tend to develop heuristics, and they say, well, we got to do this, this, and that, and they're more better at it, whereas the new kid on the block, okay, I think I'll try this, let's see what happens. And it's not necessarily an intent, it's just that you look at those sorts of things. Let me just take a look at my watch here. Okay. A plot of the residual will not show a pattern if the linear model is appropriate. If we see a pattern such as over there, that should raise questions. We ought to be asking ourselves, is there something else going on? Regression wisdom. Did we do the baseball stuff last time? The number of home runs? Okay. Extrapolation beyond the range of data is problematic. Let's go back to the here. Now, let's see, looking over here at the scatter plot, the measurements begin about 25,000 and go up to be about 40,000. So that's the range of values. Does it mean that this is going to work well when someone else drives up in their, say, their maybe Leaf or maybe Prius or some of the other small cars? You don't know. Could be that you see, if you see a Prius or a smaller car, a Leaf, those are electric ones. Let's see, there's the Fit, a Honda Fit. I love the Honda Fit, except it doesn't fit me. So a Honda Fit, I'm going to guess, is about 2,000 pounds maybe. So are we going to find that we're going to get a measurement that's going to fit this line? No, probably not. You see, what you do is you have, most trucks are going to be in a particular range. You set up all your stuff with that knowledge, and you get too far outside of that, the rule's going to break down for some reason. It's always hard to know exactly why, but it often happens. If we try to use this weight in motion to predict the weight of an automobile, and it wouldn't have to be even a small car, even an SUV, would be so far out the range, we'd be doing extrapolation, and that's very risky as a rule. The other reason would be, let's see, every now and then, trucks go down the road which are carrying extremely heavy things, all right? Usually they need permission from the state to do that. They're followed by, escorts, sometimes the police. I think they did this to move some stuff from Canada, or from the U.S. to Canada involving a pipeline. And they had to block off roads and so forth and so on. There you're going to have trucks way out to scale. Would this system still work? Probably not. It would be a breakdown. You're outside the range on which you have data, and when you are using data outside the range, we're doing extrapolation. When we're using values that are within the data collection, so if we go back to here, if we have a truck that comes in, all right, and we get a measurement, say between 25,000 and 40,000, that's well within the range at which we have data, so there's good reason to believe that if we can use our methods, it will work. That's interpolation. All right. Outliers may unduly influence regression. That relates back to the Rockies and the bog. If you have one number that's way out of line, it's going to unduly influence your regression line, your correlation, and so forth. In that case, we didn't find it. But as a general rule, if you have something that's really different, it's going to really push all these values around. And that makes the use of linear regression problematic. It may not make any sense. That's something you have to think about. Highly correlated values may not be causally related. This gets back to the fact, for example, did we talk about the lengths of index fingers and your height? Did I do that in this class? Aha! Let's do the following. We'll take a break in a few minutes here. What I'd like to do is get through this so that we can go on, take a break, and then we'll be ready for chapter 11. All right, so this is, let's go down to examples. Okay. This is what the deal is here. Just move this over here. A couple of years ago, I experimented on students. You'll be happy to know that no students died in this experiment. What we did is the following. We measured the distance from here to the top of their fingers, and I measured their heights. So I had two values associated with one individual. So we had the arm length and we had the height. And so there were 12 such students, and I did volunteer to be experimented on, and I think these are my values here. I think I'm about 74 inches in my shoes. That'd be 6 foot 2 inches. Without the shoes, a little bit less. This is the length of my arm, this is our inches. Now, this is a scatter plot. It shouldn't be surprising. Either way, if you know this length, you know more about the height, or if you know someone's height, you know this length right here. Or you have a better knowledge.
So which one you choose the explanation when you choose the arm length?
This is how you do it.
Why you don't choose the height?
You take a coin. Yeah, see, the thing here is the following. These are related, but one does not cause the other. Okay? In the case of square feet, it's reasonable to think of, square feet in a home, we can think of that as somehow determining, if you will, the price of a home. But in this case here, this doesn't, determine my height. What's happening is the following. It's your genes and your nutrition, probably primarily your genes, which are both determining this and your height. So this is what these two variables, forearm length and height, are related. There's a reasonable linear relationship between them, but it's not as though I'm saying this somehow determines your height. Now, why would I be interested in something like this? Well, this is one way. There may be others. Suppose you're a crime scene investigator and you come across a bone like this. You can stick this in the equation and you can come up with an estimate of their height. Okay? And actually you could do it the other way. If you had maybe the height of someone, you could predict this. I'm not sure that would be quite as useful in most circumstances, but, you know, and I suspect criminal pathologists probably have tables like this in their books. They'll have all these bones and they'll have ways of taking the length of those and then predicting other things. I mean, they do this for all sorts of, you know, age. I don't know exactly how they determine age. They look at bone structure and so forth and so on. But if you came across a bone, say from a human, you could identify that bone, and from that you could probably get a pretty good idea of their height, maybe their weight, maybe their age, all that sort of stuff, simply from one piece of information. And you would get it by using a technique like this, where you have people, you know, sign up, we get measurements, and we end up with a regression equation. Okay. So highly correlated variables may not be causally related. Well, there's a lurking variable. In the case of this, the forearm length and your height is your genes. Blame your parents. All right. We use regression techniques only if the scatter plot suggests linearity. It may suggest linearity, and then when we're all done, we see a pattern like this. Then we start asking the question, is there something we want to correct for? Again, it's going to be dependent on the context. A response variable, say the price of a home, may be dependent on more than one explanatory variable. The prices of homes are certainly influenced by the number of square feet, but they're also influenced by the material that we use to build the house, the location, phase of the moon, who knows what else. A lot of variables often, in fact, impact a response variable. Sometimes you use what's called multiple regression. We don't do that in this classroom and the next. A lot of economists, people in finance do that sort of stuff. So that's, and finance and economics is referred to as econometrics. Let's take a break. And I think I have, let's look at this clock up here. So I have, let's meet back here at 5 minutes after, and I don't know if we'll be able to finish by, well, we might be able to finish in 50 minutes. We get out a little earlier, not a whole lot. All right. Yeah, we're going to get into the really good stuff. Gambling. Excellent. There's a rule in gambling that you always want to remember. Well, it's a rule that's applicable everywhere. He or she who has the gold makes the rules. When you go into a casino, the casino has the gold. They make the rules. The rules are you lose.